Okay, can you hear everyone on Zoom? So cool. Good morning, everyone. Well, today I'm going to speak about everything. That sounds too much, right? But you all, yeah. So you already heard a lot about gravity, quantum, different approaches, complications, huge calculations, open problems, everything in the last 4 days. Today we will see how the real universe look like and what are the challenges, what do we know, what we don't know. This is basically the gist of what I will speak about. Of course, the title is Inflationary Cosmology, but I do start with some foundational stuff. So bear with me. So I may go with some very basic notions and understanding. So time to time, I do refer to quantum gravity approaches. Well, to put it in context, so I will basically focus mainly on the point where Luca stopped. That's where I will start, the emotional point of quadratic gravity. I will take that emotion forward, but with cosmology. And surely I do make some references to Anna's lectures on EFTs, and Benjamin Alessio spoke about non-perturbative approaches in quantum gravity. We will see what non-perturbative mean in cosmology. Maybe tomorrow I will comment about that little bit. And time to time, I do make references to string theory. So that means I make all the previous speakers happy. But of course, I have challenges to throw. So, and let's say many of you want to be doctor of philosophies. So let me start the saying, what is the philosophy of these lectures? Well, let me start with a statement. Mathematics is language of physics. I want to write gravity, but yeah, let me write physics. And what is language? What is the purpose of language? Language is something we use as a tool to describe what we experience in nature or universe. So to put in context the philosophy, let me tell you a little story. There is a father and son living in a forest. Son is little, let's say 5-year-old. One day, son ran to the father saying that, father, what? Don't go outside today because there is a big cat. Father said, oh my God, stupid kid, every day make something. So he didn't listen to the kid, he went out. Then he was eaten by tiger. So what's the moral of the story? What kid saw is real, it's tiger. But he came to the father and said, it's big cat. Oh, well, let's not go to the biology. Indeed, tiger is big cat. But let's not go to that. Language is complicated, but father didn't understand and paid the price. So why am I telling this story? As I said, mathematics is language of physics, at least this is what I believe. But language is a tool you describe nature. And if you get the language wrong, physics will be disaster. So that means it is important to build the right mathematics in association with understanding of nature, and we develop it mutually. So I hope the philosophy is conveyed. That means what we do in these lectures is basically try to see overview of the universe, how to put that in a mathematical context, and we read physics from the equations. Most of the lectures I do like to derive, but I may skip few steps, but I will give some guidance to derive them. But most of them are very basic equations. So So I prepared few slides just to convey some of the important historical developments and along with some observations. Maybe after half an hour or so, I will switch to completely blackboard. So don't worry, I will move away from the slides. So, okay, the point I would like to start is a paper with a great title, Absolute Zero of Time. It's a paper written by Charles Meissner in 1969. Let me give you a context of understanding cosmology. 1948 or 53, I don't remember exactly, George Gamow was the first one who came up with the prediction of Big Bang. He not only came up with the prediction of Big Bang, he predicted from the understanding of Big Bang, nucleosynthesis and all, he predicted the cosmic microwave background, which should be there everywhere in the universe as a signature, as a proof that Big Bang must have happened. And he even calculated the temperature of cosmic microwave background radiation about 7 Kelvin, almost close to 2.7 Kelvin. Okay, so now in the present day. And from that moment, as you know, 1965 is the pivotal year for cosmology. Until that time, it was part of philosophy, then it became very real science. And it's Penzias and Wilson who detected for the first time the cosmic microwave background. Almost, let's say, 10 years after Gamow predicted. Well, the sad story is Gamow was disappointed. No one paid attention to his Big Bang prediction. He moved to biology and started to work on DNA. But of course, this power of prediction, it will be true, even though people may deny it at that point of time. So why am I bringing this history? Because this paper, the absolute zero of time, is a completely theoretical paper. But the paper starts with completely understanding of cosmic microwave background, why the universe is FLRW. That means describe universe at large scales is described by a metric which is flat FLRW. So Meissner starts with a lot of conceptual questions on understanding of universe, and he was bothered about what is the beginning of time, because indeed Big Bang prediction is CMB and CMB was found. So just 4 years later, this paper came and he was placing philosophical questions. But they are philosophy, but they are scientific questions. Okay, don't take they are not related to us. They are related to us. The questions, the discussion Meissner made are still relevant today. They are all active areas of research. So, as you all know, general relativity is a successful theory of gravity, but it does predict singularities. And Meissner classified, what do you mean by singularities? Okay, you get singularities by solving equations. Do you care? Right? They are mathematical artifact. So he classified singularities as three categories. Some mathematical artifacts are, let me write this three, let's say. Okay, if you say they are mathematical artifacts, physically they should not exist. If they should not exist, something has to replace Einstein theory, right? So you tackle singularity by modifying GR. That's one route. The second route is don't worry about singularities. Singularities will be taken care of by quantum theory. If you have quantum theory, in QED, we have electromagnetic theory, you have electric potentials 1 over R. Do you care about R equal to 0 singularity? No. At short distance scales, quantum theory comes and kick in and let you not worry about singularities. But GR is a tricky theory. It's not easily quantizable You all heard about this in the last 4 days. So, but let's say from aesthetic point of view, let's say we must have some quantum gravity. We do not know, but it will take care of singularities. So let's not worry about singularities. So quantum theory takes care of singularities. Well, Meissner used it in a funny language. One is Einstein avoids singularities. So there is another approach. Okay, you take Einstein theory, maybe something we still don't understand about Einstein theory. Einstein avoids. Then quantum theory takes care of singularity. He uses the word nature takes care of singularities. So the third approach is a somewhere in between. Okay, there are singularities. Quantum theory takes care of singularity, but be tolerant. Let's worry about them later. The thing to worry about how the universe ended up with a FLW universe. And then he went on to present, okay, so there are singularities. Maybe I will work out the singularities a bit later. So I will explain what Big Bang singularity mean and what are the other several class of solutions. Because if you, I mean, in the cosmology we have uh, in the FLRW metric, if you take standard fluids, you get singularities, and even if you take very complicated metrics, you get singularities. So we will go through that mathematically. I will explain. So the Meissner thought is the following. Suppose if you start with a very complicated space-time, much more complicated than FLRW, can we remove singularities? Well, the answer is no. It turned out to be, it's called the Meissner initial chaos. It says the following. In GR, if you start with some initial condition, you get some evolution. If you start with another initial condition, you get different evolution. But all the evolutions end up with singularities. That means you do not have evolution which gives a steady prediction. Okay, you start with any initial conditions, you get at the late time some FLRW universe. That's what we observe. But here is not such a theory. So indeed, but Meissner kept trying, and he calls it as a mixed master universe. And there are very complicated metrics other than FLRW called Bianchi 1 to 9. And Bianchi is a class of metrics. Again, they were proposed in 1940s. So Meissner was exploring this. So why I'm explaining all this is because the discussion Meissner had has great importance in the later developments of cosmology. For example, the emergence of inflation. So I'll come back to that. So, well, this is what I wanted to give as an introduction. So what we cover in here is cosmology and quantum effects in cosmology, but the another important thing, black holes and quantum effects in black holes. So in these 2 days, we cover two of the most important elements in understanding of our universe. So I just included this slide to also see the lectures which Francisco covers, because at the end of the day, black holes, cosmology, everything are all related. How they are related, history tells us a lot. So I hope it's not boring. I do go back and forth to the history because there are a lot of lessons we learn and we still have to learn in order to make progress. So in the last lecture, I do present some of the open questions which are still there over the 50, 60 years. Okay. So black holes and quantum cosmology are very much related, and they are the developments in the both fields kind of happen due to mutual exchange of knowledge. So indeed, in the early days, Starobinsky and Zeldovich, who are computed particle production in expanding spacetime, and that was, it's known historically that has inspired Hawking to think of Hawking radiation, which you will hear from Francisco. But That was 1974. Just few years later, inflationary quantum fluctuations that explains. You see the picture here. There are two pictures. This is the black hole image, shadow. Maybe you all know. This one is cosmic microwave background. So what Hawking thought is that at the horizons, quantum effects are inevitable. And indeed, quantum effects in the early universe are what responsible for the cosmic microwave background. You will learn about it in the due course. But so why I put this picture suddenly? Remember, I started with 1965 Penzias and Wilson detection of cosmic microwave background. So they had this beautiful antenna and they detected this picture. I mean, cosmic microwave background was not in green, just to indicate that it is uniform radiation everywhere in the sky. But you see a little line there. Do you guess what it is? Yeah, Milky Way, our galactic plane. So almost 40 years later, we arrive at this, which is disproving that picture is too simple. This is the actual picture. What is the difference between the two? That is uniform temperature everywhere because the detector is not sensitive enough. And this is cosmic microwave background with tiny temperature variations. And how much? Let's say delta T by T. T naught is the temperature. Let's say temperature of the cosmic microwave background, which is at 2.7 Kelvin. And the fluctuations were detected now are the order of 10 power minus 5. You see what a development. In 40 years, we detected something. Well, I will go to the scenario. This was predicted almost 5 or 6 years later than that. How do people know that? Oh, okay. Let me open it. This was a paper from 1972, Zeldovich. You see, these names you hear, Zeldovich, Starobinsky, and you will hear more people, and Meissner. These are the theoretical physicists, but with vast amount of knowledge on observations. Meissner also, although asked extremely theoretical questions, but he starts with a puzzle, which is from the observations. Why the universe is homogeneous and isotropic. Okay, maybe I should correct this statement. Universe is statistically homogeneous and isotropic. That's a right statement. Statistically, if you say homogeneous and isotropic, it's wrong. Only maybe half mark. So it is statistics. So basically, when we talk about the large scale structure, we talk about a lot of statistics. So already in the 1960s, people have been observing galaxies. Okay, millions of galaxies. There is already a lot of data, and they start to see some uniformity in the whole distribution of galaxies. And by observing all that, and there was an hypothesis which is called Zeldovich hypothesis, but even before that, there is another scientist called Harrison. These two guys made the hypothesis that can explain the whole understanding of large-scale properties of universe. So this is just a 4-page paper, but all the questions which we are still asking are all here. All this paper covers about what do we have in the universe? We have baryons, photons, well, some unknown element, still we haven't figured out, whole dark matter. And what Zeldovich asks is, okay, whole galaxy structures, and also ask a very crucial question, why there are more baryons than antibaryons? Which people have already understood, and there are already severe constraints on the ratio between baryons, matter-antimatter symmetry. How do they know? Well, know how number of photons in the entire universe, and then take the ratio of number of baryons to the number of photons. So, so the point is, GR explains almost everything except the initial conditions. So, as I said, the temperature fluctuations are basically, you can see in the CMB. So, if you want to, the way people analyze the whole data is basically Fourier transforms. Okay, let's say we have temperature fluctuations, assume spherical symmetric geometry, and you expand the fluctuations in terms of spherical harmonics. Let me call it as curly T, and curly T Fourier transform is ALM YLM. Okay, and the if you want to analyze the universe, what people do is basically the correlations of temperature fluctuations all across the sky, different angles. So this depends on, basically this will give you the so-called, okay, this is a correlation, let's say called W of theta. Let me say N1 and N2, theta is basically modulus of N1 minus N2. So you look at the large scale correlations for different angles. And if you use spherical harmonics, this is basically expanded in terms of Legendre polynomials. Huh? It's fine. I think I'll go to that. Yeah. Let me, if I'm moving too much and it's difficult for you to. Okay. So there is this CL, which is called the angular power spectrum. I will write in more precisely at a later point. But these CLs measure the amplitude of these correlations, which are basically 1 over 2L plus 1 modulus of ALM square. The point is, these are temperature fluctuations in the CMB. Let's say, so in behind all the structure formation, there is a background radiation, which is telling us about the initial stage of the universe. So everything has grown gravitationally over these initial fluctuations. So if you look at the initial fluctuations, how the initial fluctuations should look like, that is called the scale invariance power spectrum. What they have seen, the Harrison and Zeldovich in the data from 1960s, that at very, very large scales, there is no scale dependence. That means if you go to any length scale, still the structures are the same. So this is called the scale invariant hypothesis of Harrison-Zeldovich, and we will come back to that soon. And now, I'm okay. Please don't get lost. What I'm trying to explain here, the basic elements about observations, and we will go in detail about that. And so, because they are important to understand. Well, the reason is historical reason. They were first found even before theoretical foundations were formed. Okay, so what if you want to explain CMB, the cosmic microwave background? You need an initial power spectrum. Let me call power spectrum, which is a function of k. There is some amplitude, and it should usually it is something a function of k, but it's almost mild dependence. Basically, it's almost constant for any k. So we will talk about what these numbers are, but the power spectrum is uniform everywhere. This is scale invariant power spectrum. So, but does that just explain CMB? No. You need new elements called cold dark matter and cosmological constant. Funny, right? Cosmological, you need a constant to explain the data. But it's important because without these two elements, we cannot form structures. We cannot explain anything. So these two are the new elements and are the areas of unknown physics. And it boils down to 6 parameter unknowns in cosmology, which are constrained with the latest observational data. The first one is baryons, matter. Matter means dark matter, for example. And there is dark energy, which is represented by lambda. Then there is another parameter called optical depth. Optical depth is related to, well, you see the universe, you see the CMB, but can you see anything before CMB? No, because it's completely opaque. We can see the CMB because the photons which were produced in the beginning stages of the universe decouple from all the matter because all the structures formed. So these photons decoupled and they traveled all the way to us. And all the way to us, so there are a lot of physics which happens. So we need to screen out every effect that disturb these photons. Optical depth is a parameter that fixes that when exactly that decoupling happens and all. Then there are two numbers. These are the initial conditions. This is what GR cannot give. And these are essential. And these are predicted even before people even realize this cosmological constant and everything, right? So let me show you a paper from 1984. You know that the cosmological constant dark energy was found in 1998. So a lot of theoreticians are happy because there is a new challenge to work on. A lot of theoreticians are unhappy because it shows there is a positive cosmological constant. Why not negative? So, but whatever, it's not, the story didn't start from 1908. Just from understanding of CMB, for understanding of CMB requires, essentially, you need lambda term, as you see here in this abstract, and cold dark matter. It was already in 1985, almost 12 years before. And it's a prediction put forward by Kaufman and Starobinsky. You see, there is no theory here, right? What is here is basically what do you need to explain data. So there are two ways of understanding universe. One, you look at the data so closely and try to guess what can explain the data, what function can fit the data. Then another one is from theoretical questions, foundational thoughts, and a careful calculation, which we will go through. Okay. So already 1984, people know that the temperature fluctuations in the CMB should be of the order of 10 power minus 5. So it was not surprising that Kobe satellite, which was launched and detected cosmic microwave background in 1992, they have seen the fluctuations, but of course it is, where is Kobe picture? You see, 1992. So from 1992, we have evolved our understanding or detecting cosmic microwave background, but you see little changes, but more or less consistency in the picture. Okay, I'm almost ending the observational parts. Maybe we can jump to theoretical understanding of what can generate scale invariant power spectrum. Up to now, any questions? No. Okay. So let me just see if I forget any important elements. Well, I do have some pictures here, which are basically about the galaxy clusters. So I just let me convey you this phenomena, which we know in which you all must have learned in bachelor's or anything, but this is a phenomena happening in the universe. So you see, cosmic microwave background radiation, which are very, very, very low energy photons, right? Then you ask a question, these photons are traveling everywhere, all over the universe, and you detect them. Are they not disturbed by anything? You know, indeed, when they pass through galaxy clusters and everything, there are a lot of effects happen And one of the effect is called the Suenev-Zeldovich effect. It's a very interesting effect. CMB photons travel in the empty space, and they hit high energy electrons in the intergalactic dust, and the electrons transfer energy to the photons. So the CMB photons get energized by these intergalactic electrons. This is called Suener-Zeldovich effect. Well, the reason I'm explaining this is the following. This effect is most important, and it comes everywhere in all the observational studies. So it's important for you to know what it is. Otherwise, you get lost. Oh my God, it's too complicated. Let me close the book. Okay. So that's the reason I was explaining, because there is a lot of effort in detecting the cosmic microwave background. So I want to give an example of that effort, and all these images are basically how what is the intergalactic dust. You see this cloud, which is seen with the X-ray or other uh, spectra. So, okay, I yeah. Yeah, everything, if you add everything, omega B, omega M, omega lambda, they add to 1, yes. Because that comes from the Friedman equation. I think I will write, I do write. Uh, yeah. Okay, let me stop the slides to make you happy. Sorry. Yes. Okay. Where should I go here? Stop share. Okay, fine. How to remove this? See, one of the thing I do arrive at to inflationary cosmology in a quite different way, different from the traditional lectures available in the web. So this is strongly associated with historical development and also understanding of theoretical understanding of symmetries. So that's the way I would like to approach. But surely the standard explanations exist in the literature, so you can read them once you hear these. Well, I was checking one thing. So the explanations I give here, you cannot find in ChatGPT. Okay, so please pay attention. I hope I will not bore you, but there are some basic equations to be written to understand Big Bang singularity. Does everyone know Big Bang singularity? By equations. Okay, let's look at the equations. What do we have? We have the incredible masterpiece GR and some matter, let's say standard model matter. Well, cosmological constant, which we keep adding it all the time for different reasons. But the reason I'm writing cosmological constant is nothing related to dark energy. So I wrote for a different purpose. But let's look at these equations of motion of this theory. Okay. As you know, this is, well, I put MP equal. Well, there's, you should put MP square by 2, MP square here. But time to time, I do switch to the convention of Planck mass equal to 1. When I write it is explicitly, is just to remind you about the dimensions. If you do that, you get GR equations. Okay. Well, Friedman, Robertson, Friedman, Lemaitre, Robertson, Walker metrics are basic tenets of cosmology. These are the class of metrics with flat, curved, positively curved and negatively curved, spatial curvature. I think many of you must have seen this matrix. Yeah. And well, let me tell you a little story. Friedman, who has proposed this cosmology in 1922, just almost 2-3 years after Einstein. Well, when he saw the Einstein paper, he was literally crying that he knew all these things, all the Riemannian geometry and everything, just he didn't think. He was he was already by the time 70, but still he made a mark. He gave dynamics to the Einstein theory. So that's the birth of cosmology. And another interesting fact, George Gamow, who predicted the Big Bang, was a student of Friedman. So history has a lot of inspirational things which we take forward and learn, not only in life, also science. So there is flat, positively curved, negatively curved. So these are basically this K determines what's called the spatial curvature. So if you work out what is G mu nu, G mu nu is Einstein tensor. Which is R mu nu minus half R delta mu nu. I work with one index up, one index down, just to make life simpler. So now if you plug in the Friedman metric, yeah. Yeah. Well, it's basically this one. So yeah, well, this is one, and then this metric can be written as dt square plus a square d chi square f square of chi d omega square. Okay, thanks for finding out. So this is Einstein tensor. What it is combination of Ricci tensor and Ricci scalar. So we want to know what are Ricci tensor and Ricci scalar. Let's compute. It's very easy to compute. And you can even, maybe if you are lazy to compute, you can use Mathematica. You don't need packages. At the end of the day, all GR, everything, all the curvature quantities are just combination of matrices. If you know matrix multiplication, you can compute everything. Later point, I will show you a code, which is a totally dumb code. You just write matrices. You can, by writing these matrices and Taylor expansion, if you know these two elements, you can write your own code to compute all background and perturbations. Of course, there are brilliant codes like exact exist, but anyway, you can explore exact. I don't trust. I trust only my code. So if you are of my kind, surely you can explore that direction. So if we include the flat case, that means k equal to 0, okay? You have these three components. R0, 0 becomes 3h square plus 3h dot. Rii is 3h square plus 2h dot delta ii, because your metric is diagonal, right? So you only have these elements. And if you take the sum of these two, you get Ricci scalar. Should get 12h square plus 6h dot. This is delta ia, okay? You have to combine all the three components. Fine. This gives you Friedman equations, which are nothing but you match. Yeah. Oh, I hope I'm not destroying anything. G00 equal to T mu nu. I put MP equal to 1 here. I'm going quite slow here because there are crucial observations to make. So bear with me. If you write this G00, which is basically, you get the definition there, and which gives you 3h square equal to minus rho. This is 0, 0 component. What is rho? Basically, you have T00 is again a diagonal matrix. It's energy momentum tensor. You have energy density on pressure. Feel free to stop me if I'm going too fast. I presume you know this to an extent, but yeah. Yeah. This is 0, 0 component. Yeah. Yeah. I set it to 0 for the moment. I will come back to that. So the first thing is to look at equations in the flat FLRW geometry and see what they give us. So you look at II equation. Basically, you get 3h square 2h dot equal to P. And there are some interesting relations. Minus rho plus 3P gives you 12h square. 6h dot. Well, this is basically the trace equation. So if you take the trace of this equation with lambda equal to 0, you get minus R equal to T mu mu. So it's minus rho plus 3P is equal to minus R. Okay, that's fine. How do you solve these equations? These are basically the Friedman equations. So the easiest way to solve it is the trace equation. You put this to 0, for example, some matter which is satisfying minus rho plus 3P equal to 0. Well, actually, this is some when I say matter, don't take it as matter. So basically, if you impose this condition, this means radiation. There is another equation which tells you basically you have this Bianchi identity. Mm, let me write this, equal to delta. So this equation tells you understanding of fluids in cosmology, but then that's not my point. The point is basically you take Friedman equations and plug in radiation, which is basically this condition, and this already gives you a solution for scale factor, square root of T. If you compute A dot by A, which is often called the Hubble parameter, and if you compute all the curvature quantities, which is scalar, or any invariants, for example, R mu nu, R mu nu. So in this particular case, the Ricci scalar is 0 because that's the equation, right? But this 1 over T behavior gives you all the singular solutions. So this is actually Big Bang singularity with radiation. But singularity persists with whatever the fluid you take. I'm going fast here, but if you have any question, please feel free to stop me. So basically what this gives you is you get R mu nu, all these quantities blow up at T equal to 0, and that corresponds to radiation, which is also goes to infinity at t equal to 0. So remember, I started with absolute zero of time. So the absolute zero of time is in trouble. Okay, fine. It is trouble with radiation, but you can try with matter. What is matter? If you take pressureless matter, pressure is 0. Then there is the equation of state, P by rho is 0, of course. If you solve the equations, you get a solution, A naught T power 2/3. And this is a matter dominated stage. So that means if you take general relativity and you take matter, non-relativistic matter with no pressure, it already give you all the curvature invariant that blow up at t equal to 0, because if you compute Hubble parameter for this, it becomes this. Okay, fine. You say radiation matter on trouble. I put something, whatever I want. Okay, fell. Let's start with another a bit of complication. Let me put some stuff whose pressure is proportional to energy density. So I call it as W, and W is constant. Well, if you take matter, W is 0, so basically some constant. So you take some stuff whose pressure is proportional to energy density and solve the Einstein equations. Still you get singularity, singular solution, which gives you a Hubble parameter 3T1 plus W. So W is constant. So you get whatever the fluid you take, well, at least up to fluids with constant equation of states. Fluids of in general where pressure is proportional to rho. I'm avoiding W minus 1. We'll talk about that a bit later. If you take all these generic kinds of fluids, you end up with singularity. These are all classified all as Big Bang singularities, whatever you put. And of course, you can be very innovative. You can come up with several possibilities. Well, the point is not to achieve mathematical theory, but to achieve a physically reasonable theory. That means you need that whatever the stuff you put, you have to explain physically. Okay, these are all solutions with stuff. That means placing something on the right hand side of Einstein equations, right? There is another surprising solution, which is vacuum solution of GR. Well, still you put some kind of time dependent metric. What we played with here is a flat Friedman. Singularities are unavoidable in general even if you include special curvatures. But all of the Friedman cosmology is all about when you place some kind of energy momentum tensor on the right hand side of Einstein equations. So the solution which has surprised everyone is called the BKL singularity. BKL singularity is named after Belinsky, Kalatnikov, and Lifshitz. So this is a new type of singularity which was found right after something called Kasner solution of GR. Okay, the point is the following. Why do you start with metrics which are isotropic? Why not you start with anisotropy? Okay, because after all, even if you look at the local universe, you don't have anything which is in isotropic, right? Only large scales. So why do you assume that universe have to start with some symmetry like isotropy? So that was the idea behind it. Okay. So the class of metrics I'm discussing about are like this. What is anisotropy? You add 3 different evolutions to all 3 directions of space. So now if you take, for example, I to be t power something. Let me call it as t power pi. Well, the logic behind writing t power pi is, again, you see, when you look at FLRW, all the solutions are kind of power law. Keep this in mind. The words power law will appear again at a different context. So if you take this, you can completely solve Einstein equations with two conditions. P1 plus P2 plus P3 equal to P1 square plus P2 square plus P3 square equal to 1. If you place this condition, you can solve completely Einstein equations. And what are the numbers you can think of to satisfy this? Well, yeah. P1, P2, P3 minus 1/3, 2 by 3, 2 by 3. If you plug in these numbers, you do satisfy these conditions, then you solve Einstein equations completely. That means these two conditions give you R mu nu equal to 0, all components. Ricci scalar equal to 0. And of course, this is in the presence of no matter. It is just you plug in this geometry with this power law scale factors and impose these conditions, and you get a solution that satisfies Einstein equations. Of course, no matter, no cosmological constant, but still singular. Why do you call singular? You have Ricci scalar 0 and Ricci tensor 0, but Riemann is not 0, which is often expressed in terms of so-called Kretschmann scalar. That means if you have Riemann tensor, contract with Riemann tensor, you get something proportional to 1 over t power 4. I think I do have precise number for this. Ah, 64 divided by 27 by t power 4. No proportional. Let's make it exact. So because the Riemann square blow up, it is a singular space-time. So there is a similarity of this kind of metric with the black hole, which Francesco, I hope maybe he will mention. But partial singularity is like, okay, you get everything 0, but Kretschmann scalar blows up at some point in space. But here in the time, t equal to 0, absolute 0 of time doesn't exist. Okay, but what is this particular solution? If you look at this particular solution, your universe is expanding in two directions and it is contracting in one direction. So it is an anisotropic evolution of universe. So it's important we read physics from the numbers. So you plug in here, that's what its physical meaning. So Belinsky, Kalashnikov, and Lifshitz generalize this over. This is just imagining some numbers, right? What is the general solution of this simple equation? P. Okay, let me write out of my head and then I will check my notes. P1 is this one, P2 is okay. I should check my note. I don't remember by heart everything. Yeah, it's -1 U and let us check it. If you take P1 plus P2 plus P3, so maybe it should be +1. 1 plus U. Okay. You don't get it, right? So surely I have a typo in my solution. Take this one. So yeah, it. I was typing in LaTeX very crazily, so maybe in the middle of the night. Okay. So if you play this, so U is some variable. So if you write, you can write P1, P2, P3, satisfy this condition. And this is basically the BKL singularity. That's where, how much time I have? 34. Yeah, it can be anything. Well, real, of course. Yeah. Yeah. So when BKL singularity was found, and this has created this idea of how the universe must have started. And this is the origin of the Meissner paper, which has led to the Meissner initial chaos. Because Meissner explored, okay, this is already complicated, but why not to complicate life even more? Right? It was around 1965, something. Around the same time, cosmic microwave background was detected by Penzias and Wilson. So shortly before the Meissner paper, 1969. So Meissner came up with, okay, I start with a geometry which is not only isotropic, inhomogeneous. Yeah, yeah. All the all these singularities are geodesically incomplete. Yeah. Okay. So Meissner started with, okay, I destroy all the symmetries and start with inhomogeneous and isotropic matrix, which all called the Bianchi class, and I will give references in the lecture notes. I will not discuss them in detail. So the Meissner initial chaos was popular, and there were class of physicists like followed from Meissner, like John D. Barrow, started to think the emergence of universe, which is with FLRW, from very complicated space-time. And this complicated space-time, emergence of universe with from a complicated space-time can work if you specify specific initial conditions. Otherwise, you have chaos because the GR equations give you that kind of evolution. This is kind of related to the geodesic incompleteness as well. So what is the solution? How do we begin the universe? The thing is, it's what guided all the progress in physics is finding symmetries. Symmetries are the guiding principles. And it was Starobinsky in 1980. Okay, let me try and find a case opposite to the Meissner initial chaos. Let me assume universe started with maximal symmetry, and that symmetry is de Sitter. So de Sitter, what is de Sitter? De Sitter is a space-time. If you take Einstein equations and take cosmological constant, and you get a solution which is maximally symmetric. It has the same symmetries like Minkowski spacetime, but the difference is de Sitter spacetime has constant curvature, and Minkowski spacetime, all the curvatures are zero. I will write exactly what de Sitter spacetime is, but we will take a couple of minutes break. After that, I will write them. But let me establish the idea. So universe started with maximal symmetry, let's say de Sitter. But if symmetries exactly hold, universe does not exist. Remember, Murray Gell-Mann said this. Murray Gell-Mann, who was pioneer of particle physics, well, he kind of revolutionized completely particle physics by applying group theory, which is a totally crazy idea. But all the motto for Murray Gell-Mann is to find symmetries and break them. That's the what's called the universal first thought to check whether we are doing right or wrong. in our understanding of universe. Find symmetry and break. And this is what exactly Starobinsky did. Find symmetry, which is de Sitter, and break it. How does that work? Can it work in GR? Or you need modification of gravity? This is what we explore. So let's take a couple of minutes break and we'll explain. We'll go to the Starobinsky theory of inflation. Yeah. By the way, I started 10 minutes late, something like that. Huh? Okay. Just 2 minutes, maybe. Don't leave this plot. Yeah. Start to not to interact anymore with matter, and they travel to us, and that's like where the CMB signal origins. Yeah, that's very okay. Yeah, yeah. Basically, when the structure has formed, there is a radiation-dominated era. Radiation-dominated era is bunch of like huge number of photons and free baryons. Then universe cool down and then start to form atoms. When atoms form, then these photons start to get free from the matter and then they evolve and come to us. But then the point is, in all that radiation to matter domination, so you need to calculate how the photons will evolve. And this is exactly is called the transfer functions. So basically you compute everything according to GR with some initial conditions. Those initial conditions are what we talk about. Yeah. Get energy scattering from the electron, and that can change. Like, are there like is this the most dominant effect, or are there some other things that can modify the way it's photon the gravitation lensing is there are other effects. I do not think they are dominant. Surely, but I'm not expert on observations, but the other effect is like you have these photons get trapped in the gravitational regions created by the galaxies. This is basically the galaxy CMB photon correlations, cross correlations. So this is also another effect. But what you basically do is you consider all this effect and calculate and check whether you match with the data. If you match with the data, that means your standard physics is working fine. And also you try to understand, trace what is there in the universe. Suppose Zeldovich effect, where the CMB is black body spectrum. Zeldovich effect shift that spectrum a bit. But you make observations all over the sky, right? So if you look at statistical average, then you do understand that it is indeed a local effect from the inverse Thomson scattering. So okay, so we start the 2 minute after break session. So we will in the next 20 minutes, we'll try to understand again what GR solutions are telling us. You may be wondering, okay, I said already I will go to Starobinsky inflation, again coming back to GR. Okay, before going there are some observations still need to be made. GR singular solutions means you take Hubble parameter. It is inverse time. At t equal to 0, Hubble parameter goes to infinity. And your curvature scalars go to infinity. What do you mean by infinity? We don't know, right? What is it? We cannot make physical sense of infinities. There is a scale we can make physical sense of, Planck scale. So there is a regime, there is a point in according to GR where your curvatures, the space-time curvature, becomes super Planckian. Well, we all know at Planck scale, GR is not a very good theory. So at least quantum mechanics should kick in, and we don't understand quantum mechanics and general relativity together, acting together fully. So that means it is a fair hypothesis to make, okay, let us start with the universe with close to maximal symmetry, but somewhere way below the Planck scale. Let's start a regime where you have a symmetry, approximate symmetry, which is de Sitter symmetry. Let me explain what de Sitter is, right? So de Sitter is a maximally symmetric spacetime that satisfies the following properties, which has a Riemann proportional to Ricci scalar with some metric, the background metric, which is de Sitter metric. I will write what exactly de Sitter metric look like. This looks complicated, right? But there is a Ricci tensor, looks much more simple. Delta mu nu. So this is the property of de Sitter curvatures. The curvatures just simply depend on the metric with proportionality constant, and the constant is exactly related to the cosmological constant. Suppose you get this solution, if you start with GR with some constant, I put MP equal to 1. Okay. So, but what does this mean? We need to understand. I mean, this is complicated equations, right? Let's try to understand the picture of it in terms of metrics. So if we solve equations of motion with Einstein general relativity and cosmological constant, why we are placing cosmological constant? It is just to illustrate what is de Sitter. Okay, so only that for the purpose. We want to see how the maximal symmetric spacetime look like. So Ricci scalar is 4 lambda. So this means all FLRW spacetime looks like with a scale factor cosine hyperbolic of ht if you have spatial curvature equal to 1, exponential of ht if you have spatial curvature equal to 0, sine hyperbolic of ht if you have spatial curvature equal to -1. Well, let me remind you the FLRW metric in the with all the spatial curvatures. Notice that, notice about dimensions, okay? So normally when you write this metric, so the dimensions are in the scale factor. If you make the scale factor dimensionless, then the spatial curvature actually should be proportional to some, inversely proportional to some length scale. That means r is radial distance, so r square by some other distance scale, it's dimensionless. Then r has a dimension, r has a dimension. In the if you do this, basically the scale factor is dimensionless. Normally in all the textbooks we do not write it, but keep that in mind. Spatial curvature is a quantity which carries some measure. Okay. Points to notice here. If you take k equal to 1 and look at the scale factor, what is cosine hyperbolic? So scale factor goes to, in this case, scale factor goes to a minimum and then grows. If you have 0, then scale factor exponentially growing, basically like this. So you have exponential growth of the scale factor. Of course, if you assume like minus infinity to infinity, so your scale factor is growing. So, but you have two realizations of understanding universe. One is if you have a spatial curvature, that means your scale factor goes to a minimum and then grows. It looks like a bounce, but the space-time is de Sitter. Space-time is completely de Sitter. Okay. And in the other case, there is an exponential expansion. How do you understand this? Remember that Ricci scalar is 12h square plus 6h dot plus 6k by a square. So in the case k equal to 0, that is a flat case, h is constant. That means you just have this term. Ricci scalar is constant. But Ricci scalar must be constant even if whatever it is, because it's de Sitter. So if you have spatial curvature, your scale factor grows or shrinks or grows, scale factor changes with time. That means h dot is non-zero. So, but still the whole thing is constant. It's very simple to understand. Look at these 6 factors, cosine hyperbolic, compute the whole parameter, a dot by a, it is tan hyperbolic, and apply hyperbolic relations, trigonometric relations, and you get that this is still a de Sitter space. So, but I'm not discussing much about this open case. I don't know the significance of it, and I don't know if it is. There are some applications of it, but mostly these are the two cases. Well, again, understand, we start with de Sitter. De Sitter is maximally symmetric space-time. When we write metric in a particular coordinate system and find a solution, and it looks like either universe exponentially expanding or a universe that contract and expand, it's all just a realization of the choice of coordinate system, because the space-time is static. It has no dynamics because it is maximally symmetric. So there is no dynamics. It's just some coordinate system you want to write for a later applications of something if you depart from de Sitter. So if you depart from which kind of de Sitter makes huge changes in our understanding of physics. Let me, when I say static, uh, yeah, there is another way to express de Sitter space-time. let me write instead of h square, lambda over 3. This is also de Sitter metric, where you have curvatures constant, and it looks much more kind of like Schwarzschild metric, right? But of course, singularity. No singularity, there is a horizon. That's why there is a very strong relationship between understanding quantum effects in de Sitter and quantum effects in black holes, which was shown by Gibbons and Hawking in 1977. You see all these developments before even understanding of inflation. I will come back to the inflation. I keep using this word, but I hope you might have heard of it at least. Okay. So these are important elements to understand about de Sitter space. Okay. Now the point is you need to start the universe from something close to de Sitter. But of course, we put this cosmological constant just as a toy example to understand space-time. Now, the point is, from the development of singular solutions, it is clear that the GR alone cannot give any kind of evolution different from power law behavior. Because if you have matter, radiation, you get singular solutions, and they are T power something. The question is, okay, what kind of modification of GR which can allow you to start the universe with close to the maximally symmetric spacetime, but then slowly evolves from the spacetime, and then you end up with the GR-like behavior. Because that's what you want to do, right? When you modify GR, you look at what this modification is bringing new dynamics to the understanding of spacetime. Why GR is problematic? Remember that the GR, the trace equation of GR, if you don't have anything, okay, no matter, no cosmological constant, Ricci scalar is 0. That is the trace equation of GR. That means your curvature quantity has no dynamics. If you want to start universe with some understanding of gravity, something close to the maximally symmetric spacetime, that means you need to give dynamics to the Ricci scalar. That means you need to modify the governing equation for Ricci scalar. This is basically the birth of Starobinsky theory of inflation. It starts with modification of Einstein's gravity by adding R square term. Luca already explained you what are the fundamental motivations for to do it. And in the due course, I will also try to enlighten you with more reasons to think of such a modification of gravity. But the point now we concentrate in the next few minutes is just if you have such a modification, you write Einstein-Hilbert term plus R square. Naturally, you ask a question, right? Okay, when the Einstein-Hilbert term is dominant, when the R square term is dominant, okay, that's very natural question. So if you have two terms, I want to find when this guy is more and when this guy is more. So this is a natural question. So in this modification, remember that Luca already explained this to you. So R square has dimension 4. So this F0 is a coefficient. It is dimensionless. If it is anything which is dimensionless, should be some ratio of two-dimension full quantities. It's nice to write it that way. It doesn't have to be. Okay? I will write it that way, but there is a meaning to it. We will learn it later. So there is this dimensionless coefficient. There is Planck scale. And I write it's 6m square. It is ratio of two mass dimension squares. So it is still dimensionless. Well, this is a scale which is much less than Planck scale. Let's make it as an assumption. Why? As I already explained you, if you have singular solutions, at some point you've hit Planck scales. You get disaster, which is singularity. But we need to understand the universe. Let's say, let's try to understand the universe from an evolution of from a most symmetric stage, which is de Sitter, and that we place that stage at way below the Planck scales because we do not fully know the quantum gravity. We do not, I mean, this is not full quantum gravity, right? This is some modification of general relativity. And to make sense of whatever you get from here, to make sense of it, you need to assume is somewhere, it is playing a role somewhere below the Planck scale. At least it describes evolution of universe at some low curvature regime, and the low curvatures below the Planck scale. Logic number one. Physics close to symmetry, but at energy scale way below the Planck scale. Let me not use the energy. At curvature scales, way below the Planck scales, whatever it is. So read it that way. And the second, this M is the mass scale that describes an additional degree of freedom in the theory. Remember, Luke already explained that GR has 2 degrees of freedom, 2 polarizations of graviton, and this theory has an additional degree of freedom, and this is the mass of that additional degree of freedom. You get it if you compute propagator around Minkowski, and you get to understand this, but we will see that how this additional degree of freedom is kind of emerging. So this is mass of the additional degree of freedom, and this additional degree of freedom, we call it a scalaron. So M is mass of scalaron. So because I already declared that this theory way below the Planck scale, you expect that the mass of the scalaron to be way below the Planck scale, right? Which is the assumption. So the logic is here. You start with a theory which is not at the fully Planck scales, way below the Planck scale. You want the theory to play a role way below the Planck scale, and you want the degrees of freedom to have masses way below the Planck scale. You compare masses with masses, okay? So once you do that, you already get to a regime when, because you already see that when M is much less than Planck mass square, this coefficient is huge, okay? But then you get to a regime when R, which is scalar, much greater than M square. So you take this term, it has, let me write it here. So it has MP square by 6 R by M square R. Let me put the 6 inside, maybe 3 inside and 2 outside, just to compare with the GR term. So when this R is much greater than 3M square, to make it precise, this term is dominant naturally. And what is the evolution of the universe when this term is dominant? Is the first point, first question.
Sorry, there's a quick question online.
Yeah.
Is the scalaron the same thing as an inflaton?
It is equivalent, but we will come back to that. I will answer this question. So basically, here we modify gravity, and this is there is a new gravitational degree of freedom. Why we modify gravity? We modify the Einstein-Hilbert-Lagrangian with more geometric terms. Geometric means Ricci scalar, describes the curvature of spacetime. It is geometric Ricci scalar square. So a degree of freedom coming from this modification is historically called scalaron. And it is indeed, if you write it in Einstein frame, it is named inflaton. But we will go back to the Einstein frame later. The first is to understand from the gravity point of view, if you add a new degree of freedom, how your picture of universe is changing. Does that answer the question? Hopefully, yeah. So I have 8 minutes, 5 minutes. Okay. What happens to the universe when Ricci scalar is much greater than 3m square? And obviously, the second scenario is when Ricci scalar is much less than 3m square, this term is subdominant, you get GR dominance. That means you can start the universe when this term is dominant and see if that starting point is giving us evolution to GR. That's what we want, right? Because GR is a theory which works very well. And why do we modify GR? We modify GR because we cannot explain the initial conditions of the universe from GR, which is basically the initial conditions needed to explain the large scale properties of the universe, large scale structure. There is a scale invariance. Why the universe look more or less the same at very, very large scales is something, a puzzle, which is a motivation, one motivation from observation point of view to think of this. But I already told you the theoretical motivations is basically to find symmetries and break symmetries. And another strong motivation, Luca explained, R square term is needed is if you want to make a significant step towards quantum gravity from foundational point of view. There is another motivation. I hope I have a couple of minutes time to explain this motivation. You see, what is nature? Nature is basically standard model, right? We are all made of standard model degrees of freedom. Hopefully not dark matter. So, but standard model degrees of freedom are basically the standard model theory, which is built on quantum field theory. So we know quantum fields exist, right? GR is classical theory of geometry. When you place quantum fields and GR together, the first calculation tells you that it's called the developments of conformal anomaly, which tells you that R square term kind of emerges. Of course, not with this whole new Hughes coefficient, but surely when the point is the following: you start with known principles, and you get something, and you take hint from what you are getting, and then explore from that hint. Okay, what it will give new, and R square term keep appearing in all the QFT based calculations. And that is another strong motivation. So we do not leave any hints which will lead us to new physics. That's the third motivation. So first is observation, second one is symmetries, then third one is QFT. Everything leading us to this Lagrangian. Okay, so after the coffee break, we will explore how the universe will unfold from these equations of motion. We will solve them. They are easy to solve. We will solve analytically, which are basically first solved by Starobinsky in 1980. It's a very elegant solution. We will derive that very carefully and see what happens to the universe. Thanks.